Hello everyone, this is Todd Daniel, your instructor for Basic Business Statistics. This is a day in which the university has canceled classes, and so I am doing this lecture from home. I had a different co-worker the first video, and this time I have my other little buddy hanging out with me. We're going to talk to you about variability in distributions. So let's get started by reviewing what we've already learned about variability and its relationship to central tendency. And as we do that, my coworker has some napping that needs to get done, so I'm going to put him back. There you go, little buddy. He's got his own office right there. And we're going to talk some more about variability and central tendency. Two distributions may have the same mean, but different variability in their numbers. So a measure of location, the mean, the median, the mode, we'll focus just on the mean for right now, is more reliable when variability is low and the scores are very consistent. How then can we measure variability? I'm going to walk you through a number of ways that we might get there. I'm going to start with one that you might not really think about as a measure of variability, but really it does show us some ideas about spread in a distribution. It's called percentiles. So percentiles report the spread of the data across specific intervals. They're often used with measures like college admission scores or performance scores, in which we want to say that a given individual or job applicant has scored at the 45th percentile or the 81st percentile or the 99th percentile. This gives us a way of measuring relatively where they fall against all other students or all other job applicants. The word percent means per 100. Just like a penny is 1 cent, it's 1/100th of a dollar. Cent is referring to hundredths. So we can use percent as per 100, or we could actually create smaller intervals, 3 or 4 or 5. If we use 4 intervals, that is called a quartile. If we have 5 intervals, that's a quintile. 10 intervals is a decile. These are all ways of describing groupings of numbers within a distribution. Let's focus on quartiles for a moment. Quartiles are percentiles with 4 intervals. Q1, or quartile 1, is the 25th percentile. It's the lowest 25% of scores. Q2, or quartile 2, is the 50th percentile. Q3 is the 75th, and Q4 would be the maximum quartile, up to 100%. We're going to use quartiles extensively when we learn about the 5-number summary and the use of box plots, which we'll do next week. Let's talk about another measure of variability for a distribution. This is very simple. We could just take the highest score and the lowest score, find the difference between them, and that tells us something about the range of scores in our distribution. It's called the range, and it is a great, quick, and easy measure of variability. But it does have one major drawback, and that is that the range is highly susceptible to outliers. If we have 10 scores that range from 2 to 8, and then we add an outlier score, that is 45. We've now taken our range, 2 to 8 would be range of 6, and we've blown it out with that outlier. That outlier greatly distorts our range. So how could we get around that or fix that? Well, another option is called the interquartile range. This is where we don't consider the full range of the data, but the range of the middle 50% of the data. We would do this by dividing our scores into quartiles, Q1, 2, 3, and 4, and then getting the range not of the lowest to Q4, but rather Q1 to Q3, the middle 50% of the scores, quartile 1 to quartile 3. This would not be affected by outliers. If we add that 43 to our data set, it doesn't affect the middle 50% of the scores at all. No matter how large the outlier might be, It will not touch the middle 50%. So interquartile range is much more stable. How then can we calculate the interquartile range? Here we have a data set of 10 scores, one of which you will notice is an outlier. Here's how we would go about creating the interquartile range. First of all, we would do a median split to divide the upper 5 and the lower 5 scores. So we're going to divide it right down the middle. Our median falls between scores 3 and 4. We would average those. Our median would be 3.5. Given that, we will then do a median split on the lower half of our distribution. In the lower half of our distribution, the median score is 3. In the upper half of our distribution, the median score would be 9. Now we can compute both the range and the interquartile range. The range would be the highest score, 20, minus 1. Our range then is 19. But what would be the interquartile range? That is 9 minus 3, which would be an interquartile range of 6. And if we were to change that outlier of 20 to 200, would that affect the range? Absolutely. But would it touch the interquartile range? Not at all. That's why I say the interquartile range is more stable. Well, these are easy, quick measures of variability, but they all have some pretty serious drawbacks, especially with outliers. So now we're going to examine some mathematical ways of getting to measures of variability, specifically the variance and the standard deviation. So for this example, we're going to use a smaller data set, one that we will create similar to the dog toys data set we've used before. In this case, we survey a smaller number of dogs and we ask them, how many dog toys do you own? We get these values from 6 dogs and their values are here on the screen. How do we get a mean of these scores? Add them up and divide by n. We add up each of the scores. The sum of x is 30. And we divide our 30 scores by the total number of scores, which is 6, giving us a mean of 5. The average dog owns 5 dog toys. But how would we measure the variability of these numbers? Well, there are ways that we could go about using math, and the one that would seem to make the most sense is actually the wrong way to do it. It's called the mean average deviation. And it's absolutely the wrong way to calculate variability. And I'm going to show you why. It would make sense that if we want to know variability around the mean, we could create deviation scores simply by subtracting each score in our data set from the mean. This is going to give us some deviations higher and lower than the mean. If the scores are very consistent, we'll have deviations of 1 and 2 and 3. And if our scores have a lot of variability, we'll have deviations of 6 and 8 and 10. But they'll be distributed around the mean. That makes the most sense. Let's just add up the deviation scores. We'll divide by n. That's our average deviation. But here's the problem with that. Because the scores are equally distributed around the mean. The mean is the mathematical center of our distribution. The scores above the mean, the deviation scores above the mean, will cancel out all of the deviation scores below the mean. Some deviations will be positive, some will be negative, and when we add them all up, they will always add up to 0. Well, that's no good. Every time you add up any mean average deviation, it always equals 0. It's enough to make you really mad. So instead, here's what we're going to do. We're going to fix our problem of having positive and negative deviation scores by taking advantage of the fact that when we square a number, it makes that number positive. 2 squared is 4. Negative 2 squared is also 4. What we will then do is square all of these deviations, then we can add them up and divide by n. Adding up the squared deviations is called the sum of squared errors, or more commonly, the sum of squares. We have created deviation scores, some of which are positive, some of which are negative. We have squared those deviation scores, and they add up to 38. The next logical step, let's just divide by n. And it gives us a value of 6.33. And this is called the variance. Now, variance is important. We're going to learn a set of techniques called analysis of variance. So variance can be very useful for us, but as a descriptive statistic, it's really hard to interpret because it's in squared units. So if we're talking about tenure on a job, how long someone stays in a job, and I tell you the average number of years is 12 with a variance of 8.6 squared years, that's hard to interpret. We need to get from squared years back into the units of measurement that we started with. Well, how can we do that? How can we get from squared to unsquared? Well, it's pretty simple. We're going to use the square root. This is called the standard deviation. It is the square root of the variance. This will put our measure of variability back into the original scale. It will be in the same scale as the mean. So we will talk about an average of 12 years and a standard deviation of 3.2 years. Not squared years. Everything is in the same units of measurement. How then can we interpret the standard deviation? Remember, standard deviation, it's measure of variability, so it's going to show us how consistently the scores stack up around the mean. If you have a small standard deviation, the scores will be close and consistent, low variability. A large standard deviation is high variability. The scores are far apart and inconsistent. When variability is high, then predictability is low. If you choose a number at random from this distribution, when variability is high, large standard deviation, that score could be very far from the mean. On the other hand, when standard deviation is low, all of your scores are tightly packed around the mean. Any score that you choose at random is going to be close to the mean or representative of the data set. What's a way that we might interpret the standard deviation in the real world? Well, given that we're out of school today because of the weather, let me use a weather-related interpretation. Kansas City and San Francisco each have similar average temperatures. The average high in San Francisco is 63.9. In Kansas City, it's 65.9. I've also added Springfield, Missouri as another form of comparison. The average low in San Francisco is 50.7. The average low in Kansas City, 47.4. And so if you knew nothing more than just the averages, you might be forgiven for thinking that the weather in San Francisco is very close to the weather in Kansas City. Two very similar weather patterns. But when we look at the variability in these two places, we see that Kansas City has much more variability in its weather than does San Francisco. In other words, any random day that you went to San Francisco, the temperatures in San Francisco are going to be pretty close to the average. Whereas in Kansas City, depending on what time of year you go, it could be freezing and icy, like it is today, or it could be really, really hot. In fact, if we look at the record highs, in San Francisco, 102 versus 113 in Kansas City, and the record lows, in San Francisco, 27, but in Kansas City, negative 19 degrees. Another way of interpreting this variability is to consider towns with the most variability in their weather and the least variability. The number one city with the most variability in its weather is Springfield, Missouri. Here in Springfield, you could have a warm day. In the middle of the day, it could be very cold at night. The temperatures change dramatically in Springfield, similar to Kansas City. But San Francisco, as well as other places in California, have very consistent temperatures. In fact, they are in the top 10 cities with the least amount of variability in the weather. And that is how we interpret variability in the real world. So there's one other measure that I want to tell you about. It's called the coefficient of variation. This indicates the size of the standard deviation in relationship to its mean, but then expressed as a percentage. This allows you to compare variabilities or standard deviations between distributions. As we've seen in other examples, we may get numbers like the mean and standard deviation that are very useful for interpreting a specific distribution, but they can't be compared. The coefficient of variation allows us to make those comparisons. The formula is the standard deviation divided by the mean times 100. And we add the percent sign to give us a percentage. Therefore, we need to know how to compute these measures of variability using Excel. We're going to use the same dog toys data that we used in the previous example. In fact, we're just going to pick up where we left off. So here I am on tab 2 in the Dog Toys 2 dataset for week 5. You see we've already added the values for mean, median, mode, and geometric mean. So now we can add formulas for variance, standard deviation, and the coefficient of variability. Well, let's get started with our variance. Place your cursor in cell F7, and this is where we're going to type our variance formula. Starts with an equal sign, and the variance is var.s. This is the variance for the sample. This is one that we can use to estimate a population parameter. Remember that our data are on B2 to B51. So we'll type B2 and then use either Command T or F4 to make that an absolute reference, colon B51, again F4 or Command T. Hit the Enter or Return key, we get a variance of 17.6. To create the standard deviation, we will do really the same thing. So let's save ourselves a step. Let's drag the variance formula down 1, and we will change the name of the formula from variance to stdev.s. Our standard deviation, or the square root of the variance, is 4.2. We could have gotten here also by just calculating the square root of the variance using the equal sign SQRT formula. Now let's compute that coefficient of variability. That coefficient is the standard deviation, which we find in cell F8, divided by the mean, which we find in cell F2. Enter. This coefficient should be expressed as a percentage, and that's why I didn't multiply by 100. Just click on the percentage option, and now we have the percentage for that coefficient. So now let's calculate some quartiles. You can see in the data set that I've written quartile 3 times and then put the numbers 1, 2, and 3 beginning in cell E11. We're going to use that 1, 2, and 3 for the calculation of the first, second, and third quartile. In cell F11, type equal sign quartile EXC. Again, we will be using the data in B2, make that an absolute reference, colon B51. Again, absolute reference. Comma, and then let's refer back to first quartile, which is in cell E11. Close with a parenthesis, hit return. Now we have the first quartile. And this is going to be easy. To create the second and third quartile, simply drag our formula down, and we've completed our quartiles. So that is how we can calculate our variability using Excel. Let's do the same thing using JASP. If you've closed JASP, then you can reopen it simply by double-clicking on that JASP file that we saved when we saved our dog toys in the last video. When you've opened JASP, we're going to pick up where we left off, which means you wouldn't need to re-click on the Descriptives tab, but if you wanted to, you could do that and then continue to follow along. So we have reopened our data set. All of the work that we've done previously has been saved for us. Our variables are still in the variables box. All of the measures of central tendency are still selected the way that we had left them. So let's now add our measures of variability or dispersion. Under the dispersion options, let's recheck that standard deviation and the variance. We'll get the interquartile range and the range, and now we can turn off minimum and maximum. Next, we'll get our quartiles. As we click, you will see the results appearing in the results pane. We have the mean, median, mode that we had selected previously, and now we've added the standard deviation, the forms of the range, and the quartiles. So now you can see just how easy it is to calculate measures of central tendency and variability using JASP. I want to wrap up with a summary of what we have learned. The whole point of this lecture has been describing distributions. You recall that we have categorical data, which would be nominal and ordinal, also called qualitative data, and we have continuous data, also called quantitative or numeric data. For our categorical variables, the measures of location that we would choose, we would use the mode for nominal variables, and we would use the median for ordinal variables. We do have the option of using the mode with ordinal variables, but we cannot use the median for nominal variables. The first step in calculating a median is to put the scores in ascending order, and nominal variables do not have an underlying order. For measures of variability, we tend to use the range or the interquartile range with these categorical variables if we use anything at all. We'd probably also use percentages or frequencies, which we could consider some measure of variability. Now, for continuous variables, the measures of location or central tendency would be the mean. Unless we have highly skewed data, we might have to use the median. We're going to prefer the mean whenever it can be used with our scale level data. We also have options for things like a weighted mean or a geometric mean, depending on the specificity of the situation and the variables that we are measuring. For variability, the options are variance and standard deviation. If we're reporting descriptive statistics, we would report the mean and the standard deviation. We also have options for percentiles and quartiles. Well, thank you so much for watching this video. My coworkers also thank you for joining us today, and we all hope that you enjoy your snow day. Get the most out of it, watch these videos, enjoy it, and hopefully I will see you in class soon.